let's look at how to solve for x with exponential and logarithmic functions. So your first step is to isolate the piece that has the x in it. So usually that x is either up in the exponent or it's the input for the log function, okay? So it's kind of stuck as an input in something. And so we're going to move everything we can away from it. And then we're going to free x from being stuck as the input. So if your x is up in the exponent, we'll use natural log or common log and the law of logs to bring that x down out of the exponent. And if x is trapped as the input for a log, like it is here, then we'll either use 10 or e. So e we would use with ln, and the property of inverse is to free the x. Okay, so that's kind of our plan. So number 33, 3 to the x is equal to 17. So we just want to compare this really quick to 36. This is 5 times 6 raised to the 3x equals 20. So here, my x isn't isolated because I'm multiplying by this 5 out here. Okay, so I would need to do some work on this one. But on this one, the piece of the x has already been isolated for me. So I'm done with step 1 and I can go straight into step 2. And since x is up in the exponent, I can use either ln or common log to get that out of the exponent. My natural tendency is to use ln, but you're certainly welcome to use common log instead if that's kind of what you're used to doing. So I'll apply ln to both sides. And I will use the law of logs to bring the x down in front. So I have x times ln of 3 is equal to ln of 17. And then to solve for x, I'll just divide both sides by ln of 3. So I get x is ln of 17 divided by ln of 3. Okay, and if I wanted to know what that's equal to, I can take ln of 17 and oops, close those parentheses, and then divide that by ln of 3. And I get that that's about 2.58 if you're looking for the decimal approximation there. Okay, so this would be an exact answer. This would be an approximation. All right, number 34, 4 raised to the 2x plus 3 is equal to 1. So again, I don't see anything else outside of this piece going on. So my x has already been isolated here. So I'll go ahead and apply ln to both sides. So ln of 4 to the 2x plus 3 is equal to ln of 1. And we know that ln of 1 is equal to 0. So I'm actually just going to replace that with what it's equal to. That gives me 2x plus 3 in parentheses, ln of 4 is equal to 0. And then I'm going to divide both sides by ln of 4. And 0 divided by ln of 4 is 0. That's kind of nice. That leaves me with 2x plus 3 is equal to 0. So if I subtract that 3 over, I get 2x is equal to negative 3, so x is negative 3/2. All right, and then number 15, 3 raised to the 1 minus 2x is equal to 243. So I would love for you to pause the video and give that one a try now that you've seen a couple of those. Okay, so let's go ahead and solve that and see if you got to the right place here at the end. So my x is already isolated here, so I'll do ln of both sides. So ln of 3 to the 1 minus 2x is equal to ln of 243. That gives me 1 minus 2x times ln of 3 is equal to ln of 243. And then I'm going to divide both sides by ln of 3. So I'm isolating that 1 minus 2x there. 1 minus 2x is equal to ln of 243 over ln of 3. Okay. And I know there might be some temptation to say, oh, maybe I can take 243 and divide it by 3 and call it just one natural log. You can't do that, unfortunately. So it does need to stay like this. You can put it in a calculator and get a decimal approximation. And then I'm just going to finish solving for x here. So I get negative 2x is equal to ln of 243 divided by ln of 3 minus 1. So I subtracted this 1 over, and then I'll divide by this negative 2. Okay, so I get ln of 243 over ln of 3 minus 1. That's my whole numerator divided by negative 2.